This is problems 31 through 40. So which of the following statements is true? It is helpful to examine your data before deciding to run a one or two-sided hypothesis test. That is an ethical question. And the answer is we're not allowed to do that. Does it happen in real life? Yes. But good statisticians would not do that. You would determine before you set up your experiment, you determine what you're going to do. So you don't look at the data. Looking at the data is cheating. It's like peeking at your birthday presents. You're not supposed to do that. If the p-value is 0.05, the probability the null hypothesis is correct is 0.05. No, it's the p-value is given that the null is correct. There's a 5% chance we get a sample like this. So it's a conditional. It's not, hey, the probability is this. No, it's given that the null was true, this is the likelihood we'd get a sample that looked like this. The larger the p-value, the more evidence there is against the null hypothesis. That's backwards. The smaller the p-value, the more evidence is against the null. Remember, when the p is low, the HO must go. All right? If the p-value is small enough, we conclude the alternative is true. Tricky. If the p-value is small, we reject the null. We're haters. We never prove anything. So we reject the null and we're left to choose the alternative, but we don't prove that it's true. So if the p-value is small, we reject the null. That's our decision. Or that's our best way to say it. We do not use sample statistics in stating the hypothesis. This is true, and this is super important. This is why HO is written mu equals. HO is never written X bar equals. HO is written P equals. HO is never written P hat equals. Never do that. All right? The null and alternative are always written based on the population. The null and alternative will always use population values. The null and alternative will never use the sample values. They will never use sample statistics. Okay? Super important. Super, super, super important. Number 32. A survey is to be taken to estimate the proportion of voters who favor stem cell research. What is the smallest that will guarantee a margin of error of at most 0.35 for a 96% confidence interval? All right, so remember p hat plus or minus z star p hat q hat over n. This is my margin of error. They're telling me my margin of error is 0.35, which I happen to know is a typo, but I keep always meaning to change that value, but I never get it done. So margin of error 0.35. We're looking for n. We need to do our z star. Second vars, inverse norm. Parenthesis, 1 minus 0.96, close parenthesis, divided by 2. 2.053 or 2.054. They do not give me a p, they didn't give me a p hat. When they don't, I use 0.5 because that's the worst case. I'm going to divide both sides by this. And I'll go ahead and multiply this. So this is going to be 0.25 over n equals 0.35 divided by the 2.054. Square both sides. This gives me 0.25 n equals some value. 0.35 divided by 2.054, and I'll square that. And I end up getting about 0.029 equals 0.02903. Keep all your decimal places. Then I'm going to divide 0.25 by that value. 0.25 divided by this value. All right. Now I get a value of 8. Really, you're like, where's 9? I don't see 9. We always go to the next higher value. We always go to the next higher value. There is no 9. There is no 10. My next higher value is 30. So I have to use 30. All right, number 33. Which of the following is a true statement? The p-value of a test is the probability of obtaining a result as extreme or more extreme, assuming the null is true. That is the absolute definition of a p-value. P-value is the probability of getting a test statistic this extreme or more extreme, given the null is true. They use the word assuming rather than given, but otherwise exactly the same thing. A random sample has been taken, number 34, has been taken from a population. A statistician using the sample needs to decide whether to construct a 90% confidence interval for the population mean or a 95% confidence interval for the population mean. How will these intervals differ? All right, so as the confidence level goes up, the margin of error goes up, which means the interval gets wider. So the 95% will be wider than the 90%, all right? And what they said is the 90% will not be as wide as the 95. The 95 will be wider than the 90s. That's all right. Number 35, in a random sample of 450 adults, 28% said that they felt their credit card debt is too high. With what degree of confidence can the pollster say plus or minus 4% of the adults believe that their credit card debt is too high? So here's what we have. We have, first off, our formula, p hat plus or minus z star p hat q hat over n. They're telling us our margin of error is 0.04. We also know p hat is 0.28. And we know n is 450. So let's plug in everything we have and solve for z star. So we're going to solve for z star. So 0.28 times 0.72 over 450 equals 0.04. And we're going to solve for z star. .28 times 0.72 divided by 450. And I'm going to go ahead and take the square root of that, caret 0.5. So z star times this small value. So I'm going to take 0.04 and divide it by what I just calculated. And I get 1.889. Now, technically, this could have been a negative 0.04 or a positive 0.04. So I'm essentially getting a z star value of either 1.889 or negative 1.889. And I'm looking for the confidence level. I'm looking for this area. And these are my z values. So I can go do a norm CDF, second vars, norm CDF, negative 1.889, upper 1.889, mean of 0, standard deviation of 1. And I get 0.941, so 94.1%. All right, problem 36. In a random sample of 500 women, 315 said that they would rather be poor than rich and fat. In a random sample of 400 men, 220 said they'd rather be poor and thin than rich and fat. Is there sufficient evidence to show that the proportion of women would rather be poor and thin and fat is greater than that of men? So we have two independent samples because we have two groups. We have two proportions. They're asking for proportions. This is a two proportion z-test. And I want to make sure I've identified my p hat 1 and p hat 2. So p hat 1, that's the women. So p women equals 315 over 500. So this is X and N for the women. All right. And for the men, the proportion of men is 220 over 400 equals X men. Hey, that's funny. X men, N men. And they said greater than. All right. So is the proportion of women greater than the proportion of men? Because that's going to be my alternative hypothesis. So I'm going to go ahead and run to the calculator as fast as I can. Stats test, two proportion z-test, 315 in 500. And again, I don't have to show my work if I'm doing a multiple choice test, or you definitely won't have to on this one. 400 greater than, calculate. And I end up getting a p-value of 0.00757, all right? So my p-value of 0.0075 is less than 0.01. There is, and it says very strong, but there is strong evidence. Basically, I'm rejecting the null. Anytime I'm rejecting a null, there is sufficient or strong evidence. They're using the word strong. I like the word sufficient, but in other words, there is enough evidence to reject. The school superintendent, this is number 37, wants to know what percentage of property owners are willing to support an increase in school taxes. What size sample should be obtained to determine with 90% confidence the support level to within 5%. So this 5% is my margin of error. Remember p hat plus or minus z star, p hat, q hat, n equals, in this case, 0.05. We don't know p hat and q hat. So since we don't know it, we're going to use 0.5. So 0.5 times 0.5, because you always use the worst case. We're looking for sample size of 0.05. And we know we want based on 90%. Second vars, inverse norm, area, parenthesis, parenthesis, 1 minus 0.90, close parenthesis, divided by 2. Mean of 0, standard deviation of 1. So I end up getting 1.645. Dividing both sides by this. So this is 0.25 over n equals 0.05 over 1.645. I'm going to square that whole thing. This gives me 0.25 over n equals 0.05 divided by 1.645 squared. 0.05 divided by 1.645 squared. 0.05 divided by 1.645 squared. So pretty small value, 0.0009 something. And I'm going to take 0.25 and divide it by that value. And I end up getting 270.6. We're always going up to the next higher value, which in this case is 271. Number 38 is a tricky question. You need to read all the answer choices or you'll be in trouble. Now, I'm going to speed through this and not read all the answer choices, but this is why it's important to this question. When an online news magazine asked interviewers to click their agreement or disagreement, 300 out of the 1,200 respondents agreed with the statement that that the most practical way of becoming a millionaire is winning a lottery. Immediate feedback stated that 25% of the viewers with a margin of error of plus or minus 2.5% agreed with the statement. Fine print claimed that 95% confidence. What is the proper conclusion? Well, we are 95% confident that the proportion of viewers who believe that the most practical way of becoming a millionaire is winning a lottery is between this and that. That's actually a pretty good statement. All right. They said, based on what they set up, because they basically said 0.25 plus or minus 0.025. Well, that's that. So this is actually a pretty good statement. So I'm going to have to consider that because that's our definition of a confidence interval. Without knowing whether NP and NQ are greater than 10, the calculation is inappropriate. Well, we have 1,200, so 1,200 times 0.25 and 1,200 times 0.75, those are both greater than 10, so that's clearly false. We definitely know that NP and NQ are greater. Without knowing whether or not the 1,200 respondents are 10% of all viewers, the calculation is inappropriate. We don't want it to be 10%, we just don't want it to exceed 10%. Not worded very well. Could be the answer, but probably not. The Z distribution was inappropriately used instead of a T distribution. No, we're working with proportions. So because it's a proportion, it has to be a Z. So the Z was not inappropriately used. The last one, the data was not a simple random sample. That's true. This was not a simple random sample. This was very biased. This was an inappropriate sample. This was a biased sample. This is my answer. It's a biased sample because anyone could click in, all right? Those who care, this is a voluntary response bias. Biased samples are never appropriate. So because this was not a simple random sample, this was not appropriate. Our very, very first condition, a simple random sample, was not met. All right. In a well-known basketball study, it was reported that Larry Bird hit a second free throw in 48 out of 53 attempts after the first free throw was missed, and hit a second free throw in 251 out of 285 attempts after the first free throw was made. Is there sufficient evidence to say that the probability that Bird will make a second free throw is different depending on whether or not the first free throw was made? So, first off, I have a problem with this entire question. NP and NQ were not met for this 48 out of 53. And so had they said that this was inappropriate, then I would have said that that's correct. And the reason I know NP and NQ, 48 out of 53, so 48 is greater than 10, but you also had 5 misses. So 5 is not greater than 10. So this is not an appropriate question. But they asked it, and that was not an answer choice. So we have P hat 1 is 48 out of 53. So this is X1 and N1. We have a second sample, P hat 2, which is 251 out of 285. And also, I'd say these are not even independent because one had to happen for the other one to happen. So this is X2 over N2. So when I look at this, I go, it's really not something I should be doing, but I have two samples. They want me to compare them. And they're saying, is there sufficient evidence to say that the probability will make a free throw is different? Different doesn't tell me greater, that just means not equal. So my alternative hypothesis is not equal to stat test, two proportion z-test. Once again, I don't think this is an appropriate question. So now you can sit there and say, Mr. Spencer was teaching us inappropriate things on Saturday. That's probably not going to go well for me, but oh well. Hope you're laughing. 48 out of 53. X bar 2 or X2 is 251 out of 85, not equal. And I get a very large p-value of 0.60. With a p-value of 0.60, we like big P's and we cannot lie. We're not rejecting. All right. So our big p-value is greater than 0.6. So there's little evidence that the probabilities are different. I wouldn't say there's no evidence, but there's little evidence that the probabilities are different. That is our best answer. All right. All right, number 40. There are 50,000 high school students in an extended metropolitan region. As each of their students came to register for class, counselors were instructed to use a calculator to pick a random number from 1 and 100. If the number 50 was picked, the student was included in the survey. For one of the many survey questions, 30% of the students said they couldn't live without instant messaging. Are all conditions met for constructing a confidence interval of the proportion of the region's teenagers who believe they couldn't live without instant messaging? So, so out of the 50,000 students, we're choosing 1 out of every 100 students. We're choosing 1 out of every 100. So that's definitely less than 10%. You go, how do I know we're choosing 1 out of every 100? Well, 50 is the number 50 out of 100. So 50 is one number out of 100. So N is going to be less than 10%. So we're nowhere good with this. All right. We're taking a random sample because we're using a random number generator. So we also have the random sample. So we have the random sample. So that's taken care of. So random sample, N is less than 10%. We're looking good, but we need the NP and NQ. All right. So NP has to be greater than 10, greater than or equal to 10, and NQ has to be greater than or equal to 10. Well, NP is going to be 1 over 100 because we're choosing 1 out of 100. So 1 divided by 100 times the 50,000. Well, that's 500. 500 is greater than 10. That's large enough. All right, 500 is greater than 10. Well, if we chose 500, that means there's 49,500 that we didn't choose. So that's greater than 10. So NP and NQ are great enough. Consequently, all conditions are met. We used a random number table, so we have random selection. 1 out of 100 is less than 10% because it's only 1%. And we just checked NP and NQ, they're large enough.